Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series meant for the BSc Physical Sciences students who are doing the paper on applied electronics. One of the chapters you have in this paper is on quantum mechanics, wherein we started with the uncertainty principle and the derivation of the fundamental equation which goes under the name of Schrodinger, and the Schrodinger equation being applied to very many problems. That is the basis of quantum mechanics. And in today's lecture we will be talking about the Schrodinger equation applied to the particle in a box. So, the contents of this lecture are particle in a one dimensional box, potential energy of the particle, application of Schrodinger equation to the problem, boundary conditions, and finally eigenvalues and eigen functions. To start with, first of all, you should ask the question, what is meant by a particle in a box? I can consider this a particle, and you have to tell me the answer whether I can consider this a particle. This is a particle which I have taken from a box, right? This is a particle. Now, this particle that I have, this may be a chalk piece or this is something like the cap of my pen drive, the particle I have taken from a box, and is it the kind of particle with which we are dealing? We are now in the area of quantum mechanics, wherein this particle is not a particle. This is a classical particle, like I showed you a billiard ball or tennis ball or cricket ball. They are classical objects, and the point is, this particle can have all possible energies. I can keep it on the surface of the table and I can raise the energy of the particle, right. The classical is a classical particle, right. I am in the classical regime. I am talking about this object. This object can assume all possible potential energy values, or I can make it to rotate, I can make it to go along the surface of the table with all possible kinetic energies, and hence the total energy will be having all possible values, or in other words the total energy will have continuous values. Whereas, by the word quantum, quantum mechanics deals with the fact that the particles you come across in quantum regime like electrons, protons, neutrons, they can have only discrete energies, and so the crux of the problem, the objective of the problem is to show as to how the energy eigenvalues or the energies of the electrons get automatically quantized when you apply the Schrodinger equation. I will make it clear once again. You know, this is a classical object. The classical object can have any energy value, continuous energy values are allowed whereas when you go to electrons, you will have only electrons to occupy only discrete energy levels. Suppose this is one energy level, there is another energy level, there is another energy level. Whereas for a cricket ball, it can travel with any velocity, with any momentum, it can have any energy. So, the continuous energy values are allowed for a cricket ball, whereas for electrons they will have only discrete values. And so, the problem which we are going to discuss is with regard to the electrons or protons, or in general the microscopic particles, and how the eigenvalues, what do you mean by eigenvalues? The energy values can be quantized, or the quantization comes automatically in the Schrodinger equation. I will tell you in the course of time. You can recall the Bohr's atom model, where the energy of the electron is shown to be equal to minus 13.6 divided by n square for the electron the hydrogen atom, but this n comes via a postulate. Here you do not have postulates, right? You do not have ad hoc introduction of the quantum numbers, as you had in the case of Bohr atom model or in the vector atom model. In the last chapter we saw the different atom models, where we introduced very many quantum numbers in an ad hoc manner, but here there is no question of any ad hocism. You do not introduce the quantum numbers for the sake of obtaining a proper or acceptable solution. So, a particle in a box, what is in the particle in a box? A particle in a box refers to an electron in an atom, or electron in a molecule, or electron in a metallic solid, or a semiconducting material, or a nucleon in a nucleus. So, electron, proton, neutron, nucleons, they are all microscopic particles. They are bound by means of what kind of potential? Electrostatic potential, or when you go to the nucleus, it is a nuclear potential. The nuclear potential is very much different from the electrostatic potential. In the case of atoms and molecules, the electrostatic potential, the Coulombic force will come into operation, whereas when you go to nuclear physics, that is what I am going to discuss in the next chapter. In the case of nuclear physics, or when you discuss about the nuclear potential, that potential will be completely different from the electrostatic potential. Another important point to be noted down is this problem which we have chosen as the first problem in quantum mechanics. It has been so chosen so that higher mathematics is not involved. What I mean by this is when you want to solve the other problems which we will do in the lectures to come, Hermite polynomial or Legendre equation or Logger's differential equation, such somewhat difficult mathematics will come into the picture, whereas in this problem the things are much simpler. It does not involve higher mathematics, right. So, these are some of the examples. This is a particle, right. This particle will not come out of its own. You see the particle there. Will it come out of the own? You have to give some energy to take it out, right. Let us consider a potential well. I am talking about particle in a box. I will show what is a particle box is nothing but this is a potential energy as a function of distance on. Similarly, this is a classical box, whereas I am talking about a box in quantum mechanics, right. Basically, the potential energy is important. I will ask the question, you have well in your houses, right. You have got, fortunately may have water in the well, and I will ask the question whether the water will come out of its own. The water is bound to the well by what kind of potential? The gravitational potential. It is the gravitational potential that keeps water inside, but only if you give energy, you have to put a bucket and take the water out, right. It is a classical well. You know, water in the well, you know, you don't have layers of water, right. Water does not stay in layers, it is a continuous column, but here in quantum mechanics the energy values will be discrete, it will not be continuous. Okay. Then again, water will not come out of its own. Similarly, electrons and atoms will not be able to come out of its own. Electrons are held tightly to the atom or atoms. Similarly, for in the case of molecules and also in solids. How do you extricate the electrons? You see here, in the case of electrons and atoms, the energy values are discrete, but here for this classical particle, the energy value is continuous, right. So, this mouse will have continuous energy values, right. I can have I can keep the mouse here, right. So, the mouse will have continuous values. I can keep the mouse at any point, any place, right. So, that its energy is, it can have any energy, but whereas the electron in the hydrogen atom will have only discrete orbits. The electron can be found in the K shell or the L shell or the M shell, and the corresponding energies are minus 13.6 electron volt or minus 3.4 electron volt. Or you can also ask the question whether why can't you have the electron here? It is not possible, right. N is an integer, the energy is quantized, the energy of the electron can be only 13.6 divided by n square, and the n will take values like 1, 2, 3 depending upon where you find the electron. Electron can be in the K shell, L shell, M shell and so on. So, the energies are discrete. So, this is an example of a particle in a box. By this, what I mean is the electron bound to the atom. Let us go to this case, right. What do you find here? This we discussed in the last chapter, the photoelectric effect. What do you understand by this phenomenon? This is a potential well, right. Electrons are found in a metallic material, the electrons are freely moving, right, and the electrons are freely moving, they are found inside the metal, they cannot come out of its own. You would have heard of thermionic emission. By heating you can make the electrons to come out. Similarly, by photoprocess, by shining light you can make the electrons to come out. By shining light on a semiconductor you can make the electrons go from valence band to conduction band. That is the principle involved in the what? Solar cells. In solar cells, what do? You are shining light on a semiconductor and they make electrons to go from valence band to conduction band, thereby you have make some energy transfer. So, similarly, by shining light on a piece of metal and the free electrons are coming out, you see the electrons are coming out by a photoprocess. Photo means what? Light. By shining light you can extricate the electrons. Unless until you shine light, the electrons will be found within the potential energy box. Here this potential energy box that I show here is a electrostatic potential, but here the box, in this box the chalk piece or whatever be the thing, it is held by means of gravitational potential. It is a classical potential. Here the electrons are bound to the ions and other electrons. In the case of metal, these electrons are bound by means of electrostatic potential. Here also the electrons that you have here in the hydrogen atom or any atom, they are held to the nucleus by means of electrostatic potential. This is the potential well. You see the potential well here. This is also a potential well. This is a classical potential well. This is electrostatic potential well. Okay. These are examples of the potential wells. The objective of this lecture is to show as to how the energy levels are getting quantized automatically. This is a very important thing. In quantum mechanics, unlike the old quantum theory, the Bohr atom model and the vector atom model, in which you introduced the quantum numbers in an ad hoc manner, but here you will see through the introduction of the boundary condition, the eigen values or the energy eigen values and eigen functions will come automatically, right. Not only in this problem, in the other problems also the things will come automatically. Let us apply Schrodinger's wave equation to determine the wave function psi f x and the eigen values for a particle constrained to move in the region x equal to 0 to x equal to a, the one dimensional box. The particle moves freely until it hits the wall, which forces it to bounce back. The particle is assumed to have the potential energy as 0, it is a trivial problem, because to make the mathematics simpler, you assume the potential energy to be equal to 0 for the particle when it is inside the box. It is done for a mathematical simplicity, so that you do not get into higher mathematics. The aim of the problem is to show how quantum mechanics leads to quantization of what is quantization. The energy values become discrete, it is not continuous, it is getting quantized, it is becoming discrete. That is what we are trying to show. This is the problem that you have got. Now you have got this is a box, right. This box is similar to the box we showed you earlier, or you can go to your house and see the well. In the house you have got water in the well. Now I am talking about an electron in a box, right. It may be an electron or a neutron or a proton that is found in a well, and this well is not a classical well wherein come across the gravitational potential. Here the potential that you are talking about along the y axis is the electrostatic potential for electrons, whereas for nucleons it is a nuclear potential, right. So, essentially a graph drawn between the potential energy and the x axis, right. So, the length of the box is 0 to L or A, you can have anything, right. The L is the length of the box, right. The particle in a box where the potential energy, it becomes infinity at the end points. You assume the particle to move inside the box, right. The particle is found inside the box at the end point. Suppose the particle comes to x equal to 0, and similarly at x equal to L, what happens? The potential energy goes to infinity. You see in the Schrodinger equation, what do you come across? You have the equation goes like this: d square psi by dx square plus 2m by h bar square into E into psi. What is psi? Psi, you should know two things. In quantum mechanics, when you are using the Schrodinger equation, you have the input as the potential energy. Now, what is the potential energy? V is potential energy, right. Now, this V we had in the last lecture is not found because of the fact that V is 0 inside the box. That is the reason why I omitted V. So, it reduces to this particular thing. So, the V is the input. I told you in the last lectures, when the potential energy input, what are the outputs? The outputs are the energy of the particle and the wave function or the eigen function of the particle in question. So, the outputs are E and psi. So, E is the eigen value and psi is the eigen function. How do you define psi? I told you again last time, psi cannot be measured. What can be measured is psi star psi, or psi square gives the probability of finding the electron. Here at x equal to 0 and x equal to L, the potential energy goes to infinity. Now, I will ask you the boundary conditions. Where are the boundaries? This is the boundary, right. The electron is bounded inside the box. They are the boundary conditions are nothing but what happens to your psi at x equal to 0 and at x equal to L. They are the so called the boundary conditions. You are asked the question, you are asking the question, what happens to psi? Let me now ask the question, what should happen to psi at x equal to 0 and at x equal to L? You have to tell the answer. At x equal to 0, suppose I ask the question, can you have psi to be equal to 0.1 at x equal to 0? Can you have psi is equal to 0.1 or 0.2 as a value for x equal to 0? If you have some value like 0.1 for psi, psi square has got a finite value at x equal to 0. What happens at x equal to 0? The potential energy becomes infinity. So, if you assume psi to have a non-vanishing value at x equal to 0, that means what is psi star psi? It is the probability of finding the electron, right. If you assume psi to have some value other than 0, 0.1 or 0.2, then your psi square has got a finite value, then it means what is psi square? It is the probability of finding an electron at a particular point. So, the probability of finding an electron at this point has got a finite value. Supposing you say that the electron is found at this point with certain probability, what about the energy? The potential energy becomes infinity. Irrespective of kinetic energy, the total energy will become infinity. The electron will have its energy equal to infinity. Can you accept infinity as the energy for any particle in the universe? If you take the whole universe in physics, you cannot have infinity. You know what is eigenvalue? Eigenvalue is something which can be measured in the laboratory. What is the eigenvalue or the energy value for the electron and the hydrogen atom? It is minus 13.6 electron volt, right. I showed the values. So, it may be electron volt or kilo electron volt or MeV million electron volt or billion electron volt in very many accelerators, but at any rate the energy of the sun, the energy of the universe, everything they are finite. The energy can never become infinity. So, the infinity catastrophe should be avoided. By this what I mean is the wave function at the point x equal to 0 should become 0. That is the important point. In quantum mechanics, the central point to be remembered is the boundary conditions are very important. In this problem, the wave function should be made to become equal to 0 at this point x equal to 0 and similarly at x equal to L. If you have by chance, if you say that you can have finite value for psi at x equal to 0, that means there is a finite probability for finding the electron at this point with what energy? With infinite energy. No system in the universe can have infinite energy. Therefore, your assumption or your calculation is wrong. Therefore, the boundary condition that you have for this problem is psi should be equal to 0, psi is 0, psi star psi, that is the probability of finding electron at this point is 0. The probability of finding electron at this point should necessarily be equal to 0. If you have got finite probability, then as I told you, you end up with infinity catastrophe. You are assigning infinite energy for the electron or proton, that is not acceptable. Infinity can be in mathematics, but not in physics or any other science, right. So, therefore, the potential energy is 0 inside the box, the particle moves freely, but at the end points the potential energy goes to infinity. Okay, that is what I told you. By making use of the fact that the value of B is 0 inside the box, the Schrodinger equation gets reduced to an expression of this kind where V is not found. The total energy is the sum of the kinetic and potential energy parts. You have the mv square by 2, that is the kinetic energy part. The potential energy part is 0, that is nothing but m square v square by 2m, you multiply by m and divide by m. So, that becomes the momentum is is mass into velocity, p square by 2m, and p is nothing but from the de Broglie relation, the momentum p will be h cross k. Therefore, the energy becomes equal to h cross square multiplied by k square by 2m. This is the well known Sommerfeld's free electron parabola. If you look at the right hand side of equation 1, h bar is a constant, it is a Planck's constant divided by 2 pi, m is the mass of the particle. If it is electron, you have to put a mass of electron, that is a constant again. So, the energy is expressed in terms of k, k is the wave vector, and hence the energy is directly proportional to k square, right. That is what you have here. Upon substitution, if you substitute your h bar square k square by 2m, that is equal to E. So, that is your 2m multiplied by E by h bar square. You take this 2m to the left hand side, 2me by h bar square will be equal to k square. So, here the second term will be equal to k square psi, that is what I am doing here. So, the particle which is moving back and forth between the end points in the box the solution for the second order differential equation, which is d square psi by dx square plus k square psi, will be equal to psi is equal to a sin kx plus b cos kx, right. So, you can have either a sin kx or b cos kx. It is a linear combination which contains motions in both directions. What are the boundary conditions that should be applied here? This I made it very clear. Psi should be equal to 0 at x equal to 0, and similarly at x equal to a or L. L is the length of the box. For x is equal to 0, psi will be equal to b. Supposing you take the above solution, right, you put x equal to 0, right. X equal to 0 means sin 0 is 0, right, sin 0 is 0. So, that vanishes, the first term will become 0. So, your cos 0 is 1. So, your psi will be equal to b, okay. Psi will be equal to b because cos 0 is 1, sin 0 is 0, okay. Psi will be equal to b, hence psi will be equal to a sin kx in general, because b is 0, this goes, and psi will be equal to a sin kx from the general solution. So, you take this particular thing sin kx, right. The boundary condition at x equal to L. So far I have been talking about x equal to 0, right. Now you go to the other edge of the box, x equal to 0. At x equal to 0, psi will become equal to a sin kl, right. At x equal to L also, psi should be 0. Both end points psi should be equal to 0. So, your a sin kl should be equal to 0. How will you make a sin kl to equal to 0? Because the boundary condition demands your psi to be equal to 0. That means a sin kl should be equal to 0, where a is not 0, a is a non-vanishing constant. Therefore, sin kl should be equal to 0. The most important step is the following step. If sin kl were to become 0, what should happen? Kl should be equal to n pi. So, the entire problem that we are discussing, the most important step is the following step. If sin kl were to become equal to 0, the only possibility is kl should be equal to n pi, right, and n should be integer, okay. N will take values 1, 2, 3 and so on, then only your sin kl will be equal to 0. So, you should remember now kl will be equal to n pi, this is a very important step. So, what happens k square l square? So, k square l square will be n square pi square, and k square will be n square pi square by l square. From the equation 1, your k square will be equal to, you had it earlier, 2 me by h bar square. Therefore, these two can be equated, 2 me by h bar square will be equal to n square pi square by l square, or E becomes equal to n square h bar square pi square by 2 ml square. Now, what do you understand now? You should understand, your conclusion is the following: the energy depends upon n square, where n is an integer. That is how the energy eigenvalues are getting quantized. They are the expected, or they are the eigenvalues which we wanted to calculate, and we are able to show that the energy eigenvalues are quantized in the problem that we have taken up. And so, the summary of the present lecture goes as follows. The problem of a particle in a box is chosen first because of its mathematical simplicity, and to illustrate that the energy eigenvalues of the particles are quantized automatically. Recall as to how the energy of the electrons are made to assume discrete values in Bohr's model. It was through a postulate. The problem may look to be trivial, but it is a very profound problem, and we pass on to now the following questions. What is meant by a particle in a box? Give examples. what are the boundary conditions which are applied, what are the eigenvalues, what is the significance of the problem. With this we come to the end of the lecture on the particle in a box. The rest of which we will discuss in the lecture to come. Thank you.